Hello, so this is a revision video for AQA A-Level Chemistry 1.2, Mass Number and Isotopes. This is a revision video. For more detailed explanations and for full video lessons, please check the links in the description below and visit chemistrystudent.com. Isotopes are atoms of the same element, so they have the same number of protons, however, they have a different number of neutrons. This means they have different mass numbers. For example, a sample of carbon contains naturally occurring isotopes including carbon-12, carbon-13 and carbon-14. Because they're all atoms of carbon, they have 6 protons and an atomic number of 6, but carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons, given mass numbers of 12, 13, and 14. Isotopes have identical chemical properties because they have the same number of protons and electrons, however, they can have different physical properties, such as mass, rates of diffusion, and radioactivity. Because samples of an element can contain different isotopes, relative atomic mass is used to describe the relative mass of an element. It is a weighted average that accounts for the different isotopes and their relative abundances in a sample of the element. Relative abundance just being how much of the sample contains a particular isotope. Time-of-flight mass spectrometry is an analytical technique that can be used to determine the relative masses of isotopes of an element and their relative abundances, meaning we can use it to calculate the relative atomic mass of an element. It can also be used to determine the entire relative molecular mass of a compound. There are 4 main stages to a time-of-flight mass spectrometer: ionization, acceleration, ion drift, and detection. Ionization is where the starting sample is turned into positively charged ions. There are 2 main methods that can be used: electron impact, where an electron is removed to make a positively charged ion, or electrospray, where a sample is given a proton, making it a positively charged ion. The positively charged ions formed in ionization are then accelerated during the acceleration stage by being passed through an electric field. This is a really important stage as the acceleration means all ions are given the same amount of kinetic energy. Because some ions will be heavier than others due to having different masses, some will travel faster than others and therefore pass through the mass spectrometer in a quicker amount of time. This is ion drift. After this, the ions are detected by hitting a detector plate. Each time a positively charged ion hits the detector plate, a small current is generated. And the greater the number of ions hitting the detector at any one moment, the greater the current, meaning we can use the amount of current generated to determine the relative amounts of all the ions being detected, and therefore figure out the relative amounts of each isotope in our starting sample. Now, the whole idea behind time-of-flight mass spectrometry is that the heavier the ion, the slower it will travel through the mass spectrometer. This can be explained mathematically using a couple of equations. Velocity equals distance divided by time, velocity being how quickly the ion moves through the mass spectrometer. The kinetic energy of any particle moving equals half times its mass times its velocity squared. Now, in a mass spectrometer, we can time how long it takes an ion to move a certain distance, meaning we can calculate its velocity. Velocity equals distance divided by time. And we want to figure out the mass of the ion. Well, if kinetic energy equals half times mass times velocity squared, then mass equals 2 times kinetic energy divided by velocity squared. We've just said that the velocity is going to equal distance divided by time, so we can substitute that into the equation. So now mass equals 2 times kinetic energy divided by distance divided by time squared, or m equals 2ke divided by d over t squared. The combination of these 2 equations enables us to calculate the relative mass of ions being detected in the mass spectrometer, and it's really important for AQA that you can use and rearrange these as required. A graph is produced by the mass spectrometer called a mass spectrum, with the x-axis being mass to charge ratio and the y-axis being relative abundance. Each peak in the graph represents an isotope. The mz value is a mass to charge ratio. Assuming the ions being detected have a positive charge of 1, this mz value just becomes the mass of the ion being detected. And the relative abundance just shows how much of each ion there is compared to each other. For molecules being analysed, the peak with the highest mz value will be the molecular ion peak. M+, and represents the relative molecular mass of the sample, but this is covered a little bit later in the course when we look at using mass spectrometry for organic analysis. For example, the mass spectrum for chlorine shows two peaks, one for chlorine 35 and one for chlorine 37. The relative abundance for the 35 Cl is 75% and the relative abundance for the 37 Cl is 25%. So the relative atomic mass would equal 35 times 75 plus 37 times 25 divided by 100, giving a relative atomic mass of 35.5. If you're a little bit confused about this, you can think of the relative abundance as telling you how many atoms there are of each isotope in 100 atoms of the whole element. So here, for example, if you had 100 atoms of chlorine, 75 of them would be Cl35 and 25 of them would be Cl37. So the average mass of one atom of chlorine would be the total mass of all of these atoms combined divided by 100. Well, you've got 75 atoms with a mass of 35, so that's 75 times 35, plus 25 atoms with a mass of 37, so 25 times 37, and you've got 100 of them in total. So divide that total mass by 100, and that gives you the average mass of one atom of chlorine.